All right. Day 4, motion in the Earth's gravitational field from a potential energy standpoint. So in grade 11, we did a unit on gravitational fields. I know those of you that had me that first semester where I was away because of the knock on the head, Mr. Smigowski didn't actually teach gravitational fields sort of a unit. He kind of filled it in because they were kind of behind, so he kind of jammed it in somewhere else. So you didn't miss anything, it just sort of looked a little bit different. But anyways, potential energy in the Earth's gravitational field. So we're talking vertical work. Again, I wouldn't write all this down. The work done in lifting a mass, a vertical distance d, or h if you prefer, is stored inside the body as an increase in potential energy or increased gravitational potential energy. For some odd reason, they use the letter U for potential energy. I don't know why. Most kids say, why wouldn't it be EP, energy potential, or PE, potential energy? Those are all valid. For some reason, the letter U is used. UG would stand for gravitational potential energy. So it's a little bit sort of a different convention. Remember, work equals FD. Since F is equal and opposite to FW, so like when you lift something, let me make myself some room here to draw. When you lift something, if you're lifting at a constant speed, and most people do, the weight force is down, the applied force is up, and they are balanced, right? So this F, this FA that you're doing for work is equal and opposite to FD, and so the mg goes in for the F, and the D sometimes becomes an H for height, and you get U equals mgh. Potential energy, mass times gravity times height. Sometimes mgd, but that usually causes a class of grade 12s to giggle, because some of them are drinking MGDs. Yeah. Apparently that doesn't mean anything to this group, so that's good. It all depends on the class. Do I have anything else? It looks like I've got something to click on. Okay, so in other words, the formula is mgh, mass times gravity times height. A super easy formula, multiply three things together. Okay, so is this the sample that you guys have or no? I don't think it is, right? This is sort of like a sample. If you want to write it down, you can. Yeah, this should be written as a sample. Okay, so as this 5 kilogram object is dropped off an 8 meter high cliff, what happens? So right at the top, you know what, just watch. Just watch, don't bother writing. Just watch. At the top, what is the potential energy? 5 times 9.8 times 8. It has 392 joules of potential energy. How much kinetic energy does it have? 0. How come? It's not moving, it's just sitting there. What's the total energy? 392. ET, total energy. 0 kinetic plus 392 potential. Add them together, has 392 joules of total energy. Okay, so a little bit later, that's just what was on the previous screen. A little bit later, now it's at the 3 meter mark. How much potential energy does it have? M times G times H, 5 times 9.8 times 3. It has 147 joules of potential energy. It still has more potential, like you all. How much kinetic energy does it have? Does it have any? Sure. How fast is it going? Well, we'd have to figure out how fast it's going. Tanner. ES squared equals VI squared plus 2AD. We've got to figure out how fast it's going. How come I use a 5 here? How come I don't use 3? That is the change in distance. If it's at the 3 meter height, this distance here is 5. It has fallen 5 meters. Do you think kids make that mistake a lot? That would be the reason why I'm mentioning it. So 0 was its initial velocity, 2 times 9.8 times 5. It has a final velocity of 9.9, and when I take that and convert it to kinetic energy, I get mv squared over 2, I get 245 joules. So it has 147 joules of potential. It has 245 joules of kinetic. What is the total? You add them together, it's 392. Notice that they are the same. Why are they the same? Because energy must be conserved. I should have some sound effect there, right?
Yeah.
392. What happens when it lands? When it lands, how much potential energy? Oh, sorry, I'm ahead of myself here. What's the delta U? What's the change in potential energy? The final was 147. The initial was 292. It lost 245 joules of potential, but guess how much it gained? Gee, what do you know? 245 joules of kinetic. Sound effect. Note that the total energy is the same at all times. There is conservation of energy, and as an object moves, the changes in potential and kinetic are equal and opposite. That's the theory. Let's do some sounds. How many we got here? 4? Only 3. Excellent. Okay. How many people remember Rocky and Bullwinkle, the cartoon? Yes, Connor? Wow. Usually this age group doesn't.
They made a movie about it.
Oh, that's true. That's true. There was a movie. Anyways, I don't know how this question becomes about Rocky and Bullwinkle, but they're fun to think about. Rocky, the 1 kilogram flying squirrel, is initially 10 meters up in a tree, and he jumps down to the ground. Find his total energy at the start, which is his total energy at all times, and find his velocity after he's fallen 6 meters, or he is 4 meters from the ground. Is this the one where I used to have this sort of, I could just click on it. What's the first thing you do? Total energy at the start is all going to be potential, right? mgh. 1 is his mass, 9.8 is his gravity. He's 10 meters up, and I picked these numbers so I don't need a calculator. 98 joules of potential energy. Find his velocities after he's fallen 6 meters. Now, you could do it with Vs squared equals Vi squared plus 2AD, but that's so back in the past. Let's try it from an energy standpoint. How are we going to do that? If he's fallen 6 meters, that means he's
6 meters down.
Don't make me come over there. He's 4 meters from the ground. mgh. The mass is 1. 9.8, he is 4 meters. So 9.8 times 4. $39.2, of course. So, how can we find his velocity? Well, the change in potential is going to be 39.2 minus 98. He lost 58.8 joules of energy, of potential energy, which means that he gained, right? His delta EK is 58.8. He gained 58.8 newtons. Not newtons, joules. EK is equal to mv squared over 2. 58.8. Mass is 1. Velocity squared over 2. So V is going to be the square root of 2 times 58.8. Take the square root. 10.8. So it's just another tool in your arsenal, another way to do those type of problems. Is that good? Pretty straightforward? The loss of potential energy is equal to the gain of kinetic energy. Okay, this time we've got a ball. It's launched at ground level. It's being launched straight up. Find the total initial energy. Find the height of rise. Find the EK when it's halfway off the ground, and find the velocity when it's risen 100 meters off the ground. So this is kind of different. It's launched straight up. What's the total initial energy? It's being launched. Sound effect. What is the total initial energy? Well, at the start, all of the energy is kinetic, right? EKI is going to be mv squared over 2. Two times a velocity of 50 squared all over 2. 2's cancel. 50 squared is 2,500 joules of kinetic energy. Not writing this one down, Ty? Not writing this one down? Okay. Okay. I'll deal with it. 2,500 joules of kinetic energy. Now, how do I find the height of rise? This could be a gravitational, this could be a kinematics question, right? But it says to do it in an energy way. So how do I find out how high it goes? Well, when it goes up, what happens to all that 2,500 joules of kinetic energy? It gets converted to potential, doesn't it? Right? It becomes U equals mgh. All of that energy goes into potential. Mass is 2, 9.8 times the height. So the height is 127.6. That's how high up it goes. Okay, how do you find the kinetic energy when it's halfway off the ground? What is your gut telling you? Would the kinetic energy, if it's halfway up, would its kinetic energy be just half? Would it be half of 2,500?
No.
No? Why not, Josh? Or you're not sure? Like, that would be the easiest thing, wouldn't it? Halfway up, half the kinetic energy, wouldn't it? Do you kind of get the feeling that maybe that's just kind of maybe something's worrying you about that? How am I going to do it? It'd be too easy. Okay. How am I going to find out its kinetic energy when it's risen halfway up the ground? Well, we know for sure that we can find the potential when it's halfway up, right? Mass 2, 9.8. Halfway up is going to be 127.6 divided by 2. Right? Halfway up. Cancel out. Well, it turns out that it is half. There's a little bit of rounding error, but it's half. So yeah, you could have just divided it. But I want to prove it. How fast is it going when it's risen 100 meters off the ground? Could we figure that out? Part D, how fast is it going when it's risen 100 meters off the ground? Well, we're going to have to do the same thing, mgh, 2 times 9.8 times 100. $1960. It's got 1960 joules of potential. So therefore, how much kinetic does it have? 2,500 minus the 1960. It's got 540 joules of kinetic still, and now we just convert that to speed. V is going to be the square root of that. 23.2. You should have got 1350 joules of initial kinetic energy. Maximum height of rise, MGH. .9 meters of height, and find out how fast it's going when it lands on this ledge right here. I guess this is part C. So to find that out, you're going to find the potential energy it has at that height. .45 joules of potential energy. Therefore, the kinetic energy is going to be, well, let's write it this way. ET, the total energy, is the EK plus the U. The total energy is the 1350. Oh. Oh, 147. How did I get 45?
Yeah.
That was weird.
Wrong.
So the EK is going to be 1350 minus 147. $1203. And now EK mv squared over 2. 1203. Mass is 3. Velocity squared 2. $28.3. All right. I do appreciate your patience, you guys, as I've scrambled to teach 4 things in 2 days. Not a lot of classes could sit through that, so I do appreciate your ability to be able to do that. I'm just going to give you a heads up of what's coming up. Tomorrow, I said you have all the handouts. Basically, tomorrow's a work period. Friday.
Tomorrow's not a work period, it's a working energy period.
Friday, I've suggested you do the personal power lab, although I really don't care what day you do it. Again, I would recommend not heels. Please don't get hurt. Please don't spend an entire hour out there running up the stairs. You only need to do it a couple times. Again, reminder, you only need to run the bottom flight. You don't need to do the top part, right? You are going to need the meter sticks. You're going to have to measure the height of the stairs. You need the stopwatches. You know where they are. You can use your phones as well. It's more for fun than anything. Okay? And then really all I've done is said, like Monday and Tuesday, you guys have, oh no, I said Monday you should watch the Springs lesson on Schoology. Okay? And then Tuesday you've got another work period. I'm going to guess after all of that, you're going to have tons of questions. Wednesday I'm going to come in and say, how'd things go? I'll clean up some stuff. I really don't have anything else to teach. I'm not saying we're going to have a test at the end of next week. That'd be crazy. But we are starting to run out of time here, right? So you can expect a test on this probably, so probably about June the 7th, roughly. And that leaves us with 3 days of review at the end. Exam. Okay? Any questions about the next 4 days? I'm not worried with you guys in Miss Madoodle.